Per popular request, I'll start this video by saying, hello, my physics friends. So, in this video, what we're going to be doing is we're going to be looking at energy, and specifically, we're going to be looking at energy and energy held within springs. So what that means, since we're going to be looking at springs and we're going to be looking at the energy held there, we're going to be looking at something called Hooke's law. Okay, so Hooke's law is pretty simple. Well, first off, Hookeslaw. So we're looking at Hooke's law. Okay, so this is the overall concept of the notes that we're going to be, or the information we're going to be talking about in this video. So the first thing you have to ask yourself, and you have to think about again, is you have to think about what are the two types, the subtypes, if you will, of energy. Because we know that there's mechanical energy and things like that. But what were the two types of sub-energy? Well, we know that the two types of sub-energy were, so let's write that, what are the two types of energy? Well, we know one of them is going to be kinetic. Okay, and kinetic energy is the energy of movement. Okay, oops, kind of doubling up there. Apologize. So we know that's the energy of things when they move. The other type of energy that we have is we've got potential energy. Now, with potential energy, we have stored energy. So that's what potential energy is. So that's stored energy. Okay, so this is the energy that's held, that's contained in something. Now we know that we have elastic. I mean, we're talking about Hooke's law, so we're talking about springs. We know springs are elastic. So we know that there's elastic potential energy. We also know that there's gravitational. So we know that these are two of the primary types of potential energy. But it's not just limited to these. There's actually some other ones too. Things like electrical. And whenever you charge your phone, whenever you put new batteries in a remote, anything like that, you're going to be dealing with electrical energy. So when we look at that, we know that we're talking about batteries. Okay, gravitational, obviously here we're talking about height. And then elastic, we're talking about springs. We know also that there's a fourth type that we're not going to deal with too much, and we're going to deal with, or that we'll deal with in other sciences, which is chemical. And this is the energy found in bonds, and you'll deal with that when you look into chemistry. But for the sake of physics, the main ones we're going to be looking at this point, electrical will come later, but the main ones we're going to look at in this particular area is we're going to be looking at elastic and gravitational. And for these notes, since we're talking about springs, we're going to focus on elastic energy. Okay? So now that we understand what energy we've got to deal with and that we're dealing with elastic potential energy, we have to remind ourselves, what is energy? What is the definition of energy? Well, we know that energy which we will label with the letter E, is the ability I don't know what that was. Let's fix that one. The ability to do work. Okay, so that's what energy is. Well, we defined this in a previous video, and we also defined this word right here, work, but we really didn't investigate this word. We didn't really talk about what work was. So we need to go ahead and let's actually analyze what work is. So we know that the definition of work, and let's go ahead and let's switch colors here. So we know that work so erase that, try it again. All right, we know that work is how far a force moves an object. And this object could be an electron, this object can be a ball, this object can be anything. But ultimately, it's how far this force moves any object. So when we investigate it, we can sit here and we know that we've got a few things in here. So we know that we've got work. So if we were to analyze this mathematically, we can actually find quite a few things. So we know that we've got work right there. So let's go ahead and let's put that in a mathematical formula. So what is all this? How can we translate this into math? Well, we know we've got work, so work equals something. How far a force? So we've got a force right here. Okay, so let's go ahead and let's jot that down. So we know that we've got a force. And then we know that we've got an object moving. Okay, so then when we know if we've got an object moving, that we're going to have distance. Now, here's the relationship, force times distance. But distance really isn't what you want to write, because, yeah, we know what distance is, but when it comes to physics, we need to be a little bit more choosy about the terms that we use. So we actually don't want to write distance. We want to choose something else, and it might help if I chose the eraser there, so we can choose something else. And distance, we know, is reliant on something moving. So it has to change its position. So if we're going to be talking about changing position, well, then we need to have change in position. So what we have here is we have the formula for work. So that's what that is right there. That's your work formula. Work is equal to force times delta x. In other words, change in position. All right, and just like with every formula, we need a unit. So what unit? Don't know what that was. So what unit are we going to go with here? So what unit should go with this? Well, we've got work. We don't know what it is, but we know we have these two things, and we know that they're being multiplied together. So let's go ahead and let's analyze what we think it should be. So we know that the unit of force is newtons. Let's actually move this a little bit farther down here. So we know that the unit of force, we'll pick a different color too, is newtons. Okay, so we know that the unit of force is newtons. And we're going to choose another color for the next one. We know that the unit of change in position is meters. So what we have is we have newtons times meters. But we know that this unit right here isn't a true unit per se, because it's actually a bunch of units in it. So let's go ahead and let's expand that. So newtons can actually be written as kilograms times meters per second squared. So if I were to combine these things, what would I end up with? So the full unit would actually be kilograms times meters per second squared times meters. Oh, that's the wrong color. Keep the colors the same here. That doesn't want to erase. We'll scratch it out. So, times meters. Well, when we go through and we add this all, or we multiply this all out, this can be simplified into something much easier. So let's go ahead and let's simplify it. So what it's going to end up as is it's going to end up as kilograms times meters, all divided by seconds, squared. Now math tells me that I can take these and I can multiply them out. So my final unit is going to be kilograms times meters squared divided by seconds squared. And there's your unit. That's your unit for work. But frankly, that unit sucks. Screw that. Screw that. No, that horrible unit. We're not going to go with this unit because this unit is just a terrible thing to use because it takes so long to write. And if you have multiple cases of work, this is just a horrible unit to have. So it's a darn good thing that scientists and all their knowledge, and also thanks to the guy who discovered it, we have a better way of identifying this. We identify this with a unit quite simply called the joule. Spelled Joule, pronounced joule like Jewel, and it is abbreviated with a very simple J. So for once, the letters make sense. Well, they do with Newton's too, but in this case, these letters really make sense. So our unit is going to be the joule. Okay? So there's our unit. So we know that whenever we have work, that we're going to be writing work in joules. So, excellent. We have that. But let's keep looking at this because we've talked about work, but we also have to talk about energy here. We also have to talk about energy because that's what we're looking at here. We're looking at energy and we're looking at work. So how are these two related? Well, we know that energy is the ability to do work. We know that work is how far a force moves an object. So let's say I have a ball. So we have our guy here. And he has a ball in his hand. And he throws the ball. The ball moves a certain distance. Okay, we'll call this distance x. Okay, well, let's be accurate, delta x. Now, it took work to move the ball from here, this is your starting point, to here, this is your ending point. It took work to do that because a force was applied and it moved a distance. Well, to do that work, it took energy. So that means it took energy to move the ball from here to here. So the next question is, do I have, or this person, if you will, do I have the same amount of energy now as I did when I was holding the ball, or do I have less energy? Well, I have less energy because I don't see a cord coming off of this person. I don't have a cord coming off of me. I'm not plugged into the wall. I can't photosynthesize. I'm not eating at the time. So I have less energy now because I threw this ball. So that means there has been a change in energy. Because of that, we can actually amend this formula here to this. We know that work is equal to force times delta x. And that all of that is equal to the change in energy. So what does this all mean? Well, it means a couple of key things. It means that we label work in joules, and it means that we also label change in energy in joules because they're the same unit. Why? Because they're the same thing. These things are actually interchangeable. Okay? So work can be said it's just nothing more than the change of energy. The change of energy can just be said that it's just the same as work. And then either one of these can actually be said that they're also this formula. So that means we can use this relationship, this knowledge, we can actually use this to connect to other things for calculations. We can use force to calculate an acceleration. We can use change in position to calculate a velocity and things of that nature, which will become important later. So now using that formula that we've figured out, let's take it a little bit further. So we know that energy is contained in things. So let's talk more about energy. Well, one of the big things that we've dealt with is we've dealt with springs. We know that springs contain energy. You know that if you pull back on a spring and you let it, you've moved it, you've put energy into it, and then if you let it go, it releases that energy really quick. You doubt that, hold a rubber band to your arm, pull the rubber band back and let it go, it'll snap you and it'll hurt. You'll feel it. So you know there was energy in it. So the question is, how can we relate this to springs? Well, if we have a spring, and we'll just draw a rudimentary spring here, which is horrible, by the way. And yes, my artistic skills are incredible. If I were to pull this spring out, we know that the spring would get longer. We also know that the farther I pull the spring out, the harder it's going to be, the more force it's going to take. So it's going to take more force to pull the string out that far as opposed to pulling the string out this, or excuse me, I keep saying string, the spring out that far. So the farther we go, the more force it takes. We know that relationship. So we can actually apply this graphically. So let's go ahead and let's do that. So let's draw an axis we can use. So we start with our y-axis. And there's our x. So we have an axis. And if we were to label these, we know that down here, as I put more force onto this, I know that the amount that it changes, the distance that the spring will change, will get longer. Okay, so or will be greater. So the change in x, or the displacement, will get greater. So that means if I were to say that, and we investigated and we combine it with the labs that we've done in the past, we know that if we were to draw a line would look something like that. Now, maybe a smaller slope or a greater slope, but for the most part, it's going to be a linear relationship. Specifically, it's going to be a directly proportional relationship. Well, the interesting thing about springs is, while in most experiments, you're going to have control over how much force you apply, you could also flip this. Because if I were to say, instead of controlling the force, I control how far I move the spring, so I know exactly how far out I want to move the spring, and then I measure how much force is applied, you're going to have the same relationship. It's still going to be this linear relationship, this directly proportional relationship. What does that tell us? Well, we know from previous experience that whenever we have a graph and we're looking at a relationship, that this graph is going to tell us something, and specifically, the graph is going to tell us something by looking at the slope. So how do you calculate slope? Well, we all know that it's rise. So there's our rise over run. So rise over run, but in this case, the rise is the force, and the run is the displacement. And that's a horrible, horrible delta symbol there. Let's fix that. There we go. So, how can we put this into a formula so we can actually relate all this stuff? Because we want to look at energy here. Well, we know that the amount of energy that something has is dependent on all this. The amount of energy that I put into the spring, there's got to be a relationship. Well, first off, we have to understand what's going on with the spring. We know that the force is equal to something times delta x plus something. To figure this out, I'm just using, this is a linear line, so I'm just using y equals mx plus b. Now, we know that this is going to be the slope, so the slope's going to go right here, and then b is going to go back here. Well, b in this case, when we talk about a spring, we're talking about what it takes to zero the spring out. Because ultimately all springs are actually, well, not all, but a lot of springs are actually pulling in towards each other so much that if you can actually apply a little bit of force to them and they won't even move. So that's kind of like its 0 point. So we're going to kind of call that the 0 point. And that can be calculated in things, but for the sake of this this particular notes. We're not going to really concern ourselves with this too much. What we are going to concern ourselves with is what goes there. Okay? So let's figure out what goes there. So if we look at this relationship, what we're going to find is we're going to find that this slope represents the amount of force and distance, or newtons over meters, that changes as we go. So what this is saying is this right here represents how much force I have to apply to make the spring move a certain distance. Now, if you look at it, if I look here, so let's identify this with a different color. Let's say orange. If I look from this point here to this point here, so if I look between the two orange points and then I look again between the two red points, is there any change in this line? There isn't. So that means throughout this entire line, this slope is constant. Well, that becomes very important because that actually tells us what this is. We actually have a name for this. What this is called, we actually label it with the letter K. This K represents what's known as the spring constant. And all the spring constant is it tells you basically how strong the spring is. So the spring constant is just going to tell me how much pull the spring is going to give me depending on how far I pull it, or how far the spring's going to get pulled depending on how much force I apply. And so this actually gives us our equation. So our equation is actually right here. So let's rewrite that equation so it's nice and clear. So we know that the force is equal to K times delta x. And we're going to leave the 0 point out in this case. So there's your formula. Your formula's right here. That's your formula to calculate, to work with springs. And this right here, that formula right there, is what we identify, and I should write that with a capital. That's the formula we identify as Hooke's law. This right here, this knowledge, this formula is Hooke's law. This tells me everything I need to know about a spring. So, how can we apply this into energy? That's the next question. Once again, let's look at our graph, and let's say we have a spring. And we're going to identify this spring with the color teal. So here we have our spring. And we're going to say this spring has a strength, or a spring constant, of K. We're not going to put numbers to it right now because we don't really need it at this point. So let's go ahead and let's draw our line for our spring. And we'll say that line looks something like that. Okay? So here's what happens as you move the spring along. Here's how much force it uses, so on and so forth. We know that at this point right here, we've put a certain amount of energy into the spring. Okay? We also know that we'll identify the second point at purple, that we have a certain amount of energy at the spring. So everywhere on this line, we've put energy into the spring. So the question is, how much energy have we put into the spring? Well, if we actually take a look at this, and we look right here, we know that we've done work. Whoops. We know that we've done work. We've moved something here. We know that we have force. So, we know that there has been a change in energy. Well, how do I figure that out? Well, what you'll find out is that if you go back to the work formula, we know that work is equal to force times change in position. Well, look what we got here. We have force, up and down, times change in position, left and right. But what's wrong with that? If I were to multiply force, let's go with red. If I were to multiply the force, we're looking at the up and down here, by the distance, we're looking at the left and right here, what would I have? I'd have a square. The problem is, we have a line going right through the center of that square. So square isn't the right one to use. So if I get rid of this, and I actually look at the red down, and I actually look at the change down here, so here's our change in distance, what we notice is that this right here goes away, and we notice, what shape do we have? Well, we have a triangle. We have a base right here. We have a height right here. We know that force is the height. We know that delta x, or change in position, is the base. So what do we got? Well, we just plug this right into the area of a triangle. Well, we know that the area of the triangle is quite simple. It's 1/2 base times height. Well, let's replace these letters. We know that force is the height, so that's equal to 1/2. Delta x is the base, times delta x times force. And guess what? That's your formula. If I want to know the amount of energy used, so there's my delta E, and that should be a delta, not just an E. That's my delta E. That means this is also the work that I did. So 1/2 delta x times F is the amount of energy that something has. And it doesn't even, it's what it has, and that's starting from 0. So that's what we've got. We've got our energy. We've got our work. We know how much energy is stored in this thing. 1/2 change in position by force. We can do the same exact thing for purple. We now know that here's our height. We now know that here's our base. So we know that if I wanted to know the energy of this, it'd be 1/2 delta x times force. So let's put some numbers into this. Let's say at this point right here, and I'm going to put this in black just to make it simple. We'll say that we move the spring 25 centimeters, and we'll say I had to use 10 newtons of force. Let's make the numbers easy. Okay, so my force, 10 newtons. My change in position, 25 centimeters. Now, how would I do this? Well, first off, we have a problem. That's in centimeters. If we think back to our unit, we're dealing with forces here in delta x. We were going to be dealing with meters. So that unit can't work, so we have to convert that. 25 centimeters can't be used, so we have to turn centimeters into meters. Well, to do that, we just simply divide by 100, and we get 0.25 meters. Okay, so now I can use that. So we know that we have our meters. Okay, so it's 0.25 meters. We also know that we've got 10 newtons of force that was applied. How can we calculate the energy? Quite simple. Plug it in. So I know that I have 1/2. Let's go back to the color here. Let's go back to red. So I know that I have 1/2 times 10 newtons. And I know that I multiply by 0.25 meters. Let's put a 0 there, make it clear. So 10 times 0.25 divided by half, so that's 5. That's 5. Plug it into the calculator just to be safe. So 0.5 times 10 times 0.25 equals 1.25. So that means my total energy stored in that spring is 1.25 joules. That's how much work was required. That's how much energy was stored at that point. I can do the same thing for the purple. Let's say in this case, this is, switch the colors. At this point, let's say this is, judging by that, we'll say it's 25 newtons. And we'll say this is 60 centimeters. Well, let's plug it all in, and let's switch to purple in this case. So we know that we've got 1/2 times 25 newtons times, and I forgot to put a unit here. That's a big no-no. You want to make sure you use your units. Times 60 centimeters, but we can't use centimeters, so we're going to have to turn that into meters. Divide that by 100. We end up with 0.60 meters. Multiply that out. Bring up the calculator again. So, clear that out. Oops. Read that wrong. Should be multiplied. My mistake. We end up with 7.5. So we have our energy here. So we have our energy at this point. We have our energy at this point. Now, what would we say about if we went between the two? So let's say I went from red point, or point A, to point B. Will this entire thing be our energy? Would it be purple? It wouldn't, because we actually already started from 1.5 joules. So we would literally create a situation where you have to solve one and the other. We create a delta. We create a delta E, a change in energy. If I start from 0, I can just find that point. But if I don't start from 0, I've got to find my initial point. So how you solve this in that case, well, you need a final and you need an initial. So you'd have to find the energy for the final, you'd have to find the energy for the initial, and you'd have to subtract them. In this case, we know that red, this is our final energy. So our energy final, that should be a lowercase f. And actually that should be a lowercase I, my mistake. And then this is our, let's get rid of this. And this is our energy final. So we subtract them and we get 6.25 joules. There's the work. That's the work done in this case. That's the change in energy. Okay? And then using that, you can do a bunch of other calculations. So, to sum up what we talked about here, we've talked about quite a few things in this particular video. We've talked about work. We know that work is equal to force times distance, which we identified as delta x. We talked about Hooke's law. So here's work. We talked about Hooke's law, which tells us about springs. We know that the force is equal to the spring constant, which we identified as K, times the change in position, the stretch or the compression. Okay. And then we also talked about the energy in a spring. I don't know why I put that down there. And we know that the energy is nothing more than 1/2 force times delta x. Okay? So there's the energy in this ring. Okay? We also know that if we want to find the change in energy, which is equal to the work, graphically, if we want to find it graphically, we know that we can take a line, we calculate our final energy, and we subtract our initial energy. So then it becomes EF minus EI. And that gives us our work, or our delta E. So, hopefully this video helps you guys out, and hopefully it helps clarify and helps establish what needs to be known from these things when it comes to energy and springs and Hooke's law. And I know it's a lot of equations, but ultimately when you look at it, they're kind of repetitive, kind of simple base equations, simple algebraic equations. As usual, please leave any questions you have in the comments, any suggestions, and thank you for your time, and have a good day, my physics friends.